Okay, hi everyone, good morning. So welcome to the exercise class today. So for the exercise class today, I have a following plan, which indirectly relates to the problems in the exercise sheet for this week. So the plan is as follows. So first I'll talk about the time evolution of stationary states. Then I will reintroduce density matrices. So you probably already heard about them in the lecture, but we'll look at them a bit closer and motivate them and also see what properties they have. And finally, we'll also look at partial trace and what it corresponds to. And we'll look at a couple of the examples. But first, let's start with the evolution of stationary states. And for that, so essentially suppose that you have a particular Hamiltonian, and then you're able to find out the eigenstates of this Hamiltonian. Then the question is, how do these eigenstates evolve with time? And to see how it goes, let us start from the beginning and first consider the Schrodinger equation. So, which would say IH bar d big psi by dt equals h psi, where h is the Hamiltonian. For this problem, we'll consider only Hamiltonians which do not depend on t, so time-independent Hamiltonians. So consider h not dependent on t. And what are the stationary solutions of the Schrodinger equation? The stationary solutions are the solutions which are characterized by the fact that we can separate the solution in a form of a product of a function which only depends on time and a function which only depends on the position. So for stationary solution, we would have this big psi of xt would be equal to g of t psi of t, small psi. Then since we can express the wave function as a product of this functions g of t and psi of x, then let us insert this expression in the Schrodinger equation. And what do we arrive to? We arrive to IH bar d g of t psi of x by dt equals h acting on g of t psi of x. Then on the left-hand side, we can just safely take out psi of x because we're only taking derivative with respect to time. So here we are left with IH bar of psi of x dg of t by dt. And here we can take out the function g of t because we assumed in the beginning that the Hamiltonian does not depend on t. Here we're only left with Hamiltonian acting on psi of x. Okay, then let us collect all the everything which connects to the function g on the left and everything that connects to the function psi on the right. So hence we will arrive to IH bar 1 over g of t. Here we can even write the full derivative because the function g only depends on t. And on the right-hand side, it would be 1 over psi of x, h acting on psi of x. Okay. So what we have here is we have a function on the left-hand side, we have a function of t, and on the right-hand side we have a function of f. Sorry, of x. And essentially, then the only way both sides can be equal to each other for all values of x and t. So the only way for it to be so is for the both sides to be equal to some constant. And let us call this constant E. So then we can separate into two equations. So the first equation would be that IH dg by dt equals EG. Here we'll just write that this is equals E. And the second equation would be H acting on psi of x equals E psi of x. So by considering a stationary solution to the Schrodinger equation and being able to express the stationary solution as a product of function of t and function of x, we are able to also separate this differential equation into two equations. Okay, and so from the first equation, for the function g of t, what we get is IH dg by dt equals EG. I just rewrote what we had on a previous page. And from here, we can conclude that g of t equals e to the power minus IET over h bar. Of course, there must be also some constant here, but up to the normalization, because we need the states, the solutions to the Schrodinger equation to be normalized, one can show that this coefficient is actually just 1. Okay, and the second part of the equation is something that we already saw. It's Hamiltonian acting on psi of x equals E psi of x. And to find psi of x here, the functions psi of x are essentially the stationary states, the part which does not depend on time, and they are the eigenfunctions of the Hamiltonian. So to solve the second equation, you just need to find the eigenfunctions of the Hamiltonian and the corresponding eigenvalues, which would be the corresponding energies. Combining these two solutions, we can write out the general solution of psi of xt, which would be psi of x e to the power minus IET over h bar. Now let us consider the following question. So suppose that we're starting with at time t0, we're starting with some arbitrary state, which we'll label as, let's say, phi of x. And since we already know and then we want to see how the state evolves under the action of the Hamiltonian h. And since we already know that what is the basis of this Hamiltonian, so what are the eigenfunctions of this Hamiltonian? They actually form a basis. So the the eigenvectors of a Hamiltonian or of any Hermitian operator, they form a basis in Hilbert space. And thus we can just take our state at time 0 and just decompose it in terms of the eigenfunctions of the Hamiltonian. So let's say we do it with some coefficients. So if we label the eigenfunctions of Hamiltonian psi I of x, then we can write phi of x as just sum of over I, some coefficients ci, psi I of x. And then actually, because we are able to decompose our arbitrary state into the eigenstates of Hamiltonian, then it's quite clear how this state evolves under the action of this Hamiltonian. Because we know how each of the individual states evolves under the action of the Hamiltonian. And we also know like to which solution in time this each eigenfunction corresponds to, then essentially we can just directly write its time evolution. So this function phi of xt. And phi of xt would be just sum over I, ci, psi I of x, e to the power minus I, ei t over h bar, where ei's are the corresponding eigenvalues or the corresponding energy values for the eigenfunctions of Hamiltonian. So eigenvalue of psi I of x. Hence, this gives us a very easy way to understand how a state with which we start at time t0 evolves with time. So evolves as predicted by a Schrodinger equation. So to see how an arbitrary state evolves, you just need to decompose it in terms of the eigenfunctions of the Hamiltonian. And then for each eigenfunction, the eigenfunction evolves according to its eigenvalue, ei here. Choose another color. Okay, and the first exercise mostly deals with this, and also since you are able to write the time evolution for the like arbitrary state in terms of its decomposition into the eigenfunctions of the Hamiltonian, you can also, for example, write what is the expectation, what is the energy expectation for the state phi, for example, at an arbitrary time t, and how it can be expressed in terms of the energy eigenvalues. Okay, so this was about the evolution of a stationary state. Then let us proceed to the second part, which is density matrices. So we already have a description of states in quantum mechanics, right? It's just our vectors in Hilbert space. But is it enough? That's the question. So what we would like to do, we would also like to have some kind of machinery which would allow us to develop a theory of states that combines also randomness with quantum mechanics. So for example, we would like to be able to describe a following quantum mechanical situation. So imagine that I have an array of states, an array of quantum states, and then I also have a probability distribution, like separate from this array of states. And then I want to perform a following procedure. Like I want to prepare a particular state out of this array with the probability which is given to me by the probability distribution. So for example, I have two states, 0 and 1, or I am able to prepare these two states, 0 and 1. And what I want to do is, let me label as this scenario. So scenario, suppose that I have states 0 and 1, and I want to prepare, I don't even want, like, I prepare 0 with probability 1/3 and 1 with probability 2/3. And the idea is that like a situation in the lab which can happen is, oh, I had this initial probability distribution, I prepared something, but then I forgot what I prepared exactly. And so how do I describe the quantum state in that case, when I may have prepared 0 with probability 1/3 and 1 with probability 2/3? And this is exactly the situation which density matrices allow us to describe. So in this case, I would describe the final state as 1/3 0 0. So 0 ket 0 bra plus 2/3 1 1. So if we write it out in the matrix form, then this is just a diagonal matrix 2 by 2, 1/3 2/3. And again, this is just an idea of adding some randomness into quantum mechanics. And also maybe to make a comparison with the classical case, let us consider a classical system which can be in d different states. And so let me maybe draw some kind of table. So we have classical and quantum, and I'll try to draw an analogy. And in classical we have, and also we have a deterministic case and a probabilistic case. So what I mean with the deterministic case in classical settings, it's when I have a classical system which can be in one of one of states which is chosen from this array from 1 to d. So it can either be in 1 or in 2 or in 3 and so on, but it can only be in one state with certainty. We can also introduce kind of the probabilistic version, like of this classical setting, where the system can be, where we would have a certain probability distribution over the set of possible states from 1 to d, and then the system would be in the, for example, in the state 1 with probability p1 and so on. So, and then the state of the system would be characterized by just this vector of the probability distribution. And we want to make, essentially, density matrices allow us to make the same leap from deterministic to a probabilistic description in quantum mechanics. So what we mean by kind of deterministic description in quantum mechanics is that we mean that we just have an array of states in the Hilbert space, which is just the d-dimensional space such that the states are normalized. But whenever we are looking at this at the particular system, it has to be in one of these states on the Hilbert space. But then if we also, as the same as in a classical case, also additionally on top of this Hilbert space, also put up some probability distribution and say that, oh, the system is in this state with probability P1, in this state with probability P2, and so on, then what we arrive to are the density operators. And this is exactly what they're useful for. Okay, now let us look like how the density operators are characterized. Yeah, there is a question. Ah, sorry, yeah, of course it's one. I was just looking at the 0, which is above. Okay, suppose that we have, in the quantum case, a discrete distribution where state, let's say, where the state psi I, let's say, occurs with probability Pi. And let us consider in this setting the observable A. Consider an observable A. And let us calculate the expectation of this observable with respect to the ensemble that we're looking at. So we have A. And how do we calculate this expectation value? So we know that, so we can calculate the expectation value of this observable for each of the states psi I, where I goes from 1 to D, let's say, as psi I, A, psi I. However, we also know that we can, so the system is in a state psi I with a probability Pi. So we just have to sum over with the weights over I with the weights of these probabilities and with the corresponding expectation values of A for each of psi I's. Okay, then we arrive to the sum from 1 to D, Pi, and the expectation value of A for the state psi I. So here the trick that we can do is, since psi I, A psi I is just a value, it can also be seen as just the 1-by-1 matrix. And since it can be seen as 1-by-1 matrix, we can just write it out as the trace of itself. Okay. Then let us remember something from the linear algebra. Like, it's quite easy to show, but yeah, so it's quite easy to show that for 3 matrices, if we have, like, for example, matrices A, B, C, and we take a trace, then we can actually do switch the order of these matrices in their product, but still get the same trace. So trace of ABC equals to the trace of CAB. So we can cyclically change the product, but the trace will stay the same. So we will do this here, and we will put the psi, the ket psi on the left side. Because as we remember, like we can understand the psi, the Brownian kets just as vectors and A as just a matrix in this vector representation. So here then we get psi A. Then we can, since PI's and the sum are just numbers, we can just input them inside trace. And let us also put the A cyclically on the left side. So then this will be trace of A, sum from I to D, PI, psi I, psi I. This would be, and this sum inside the trace, we will call the density matrix rho. So then this will be trace of A rho. And from this example, we see why it is handy to define this object as the density matrix of this ensemble of the states of psi I with a probability distribution pi. Because this allows us to see the measurement statistics as just a function, are a function of the distribution only via the density operator. So this is the density operator. And hence measurement statistics are a function of the distribution only via the density operator. So if we have a system and we know the density operator, this one here, then we can already calculate the expectation value of any observable. We don't need any additional information about the system. And so let us look at a couple of the examples of the density matrices. So the first example are so-called pure states. So pure states correspond to the following situation. So suppose that the system S is in the state psi. And then it's we know that the system S is with probability 1 in the state psi, which means that we prepared it in the state psi with probability 1, which means that if we remember the definition of the density matrix, we have only one function, function psi I, which is equal to psi, and the corresponding pi equals to 1. So the rho would just be psi. And such states are called pure. And all other density matrices are called mixed. So essentially, if the density matrix is mixed, then it means that it cannot be described as just one quantum state prepared with probability 1. So it's always a mix of several quantum states or with a certain probability distribution over them. So now maybe let us do an example. So suppose that psi, we're looking at the state psi, which is 1 over square root of 3, 0, plus square root of 2/3, 1. And suppose that we're looking at the state of the qubit, right? So how to calculate the density matrix? So the easiest way is just to write psi as a vector in the basis 0, 1. Then we get the following column. Then to calculate rho, we need to multiply the ket psi by the bra psi. And the ket psi we already have. And the bra psi is just the conjugate transpose. So there is nothing to conjugate here, so we just write our vector as a rho. And here you can see that if we look at the sizes of these vectors, then this is a vector of size 2 by 1. This is a matrix of size 1 by 2. Then essentially, if we multiply them, then we should get a matrix 2 by 2, as expected, for the density matrix. And so if we multiply these two vectors, we get 1/3, square root of 2 over 3, square root of 2 over 3, 2/3. Okay, cool. So the similar operation can be done for any pure state. There is also, so as I said, there are all the states which are not pure, they are called mixed. But among mixed states, there is also a special class of states, which is called maximally mixed states. So maximally mixed states. So maximally mixed states correspond to the following situation. Suppose that we have an orthonormal basis V1, so on, Vd in a d-dimensional Hilbert space. So this is an orthonormal basis. And then the scenario is that we can prepare each of the states in this orthonormal basis with the equal probability 1 over d. So, and each state occurs with probability 1 over d. Then the resulting density matrix, according to how we defined it, is rho equals sum over I from 1 to d, 1 over d, vi, vi. So this is just 1 over d, sum over I, vi, vi. And actually, if you look at the sum, there are only, because if we look at the sum and then we look at how the matrix of this corresponding to this sum looks like in this orthonormal basis from V1 to Vd, we see that it's only diagonal elements. And all of these diagonal elements are 1. So essentially, this sum corresponds just to the identity matrix. So then this density matrix is just the identity matrix over D. And such state is called maximally mixed state. Well, we can see why, because each state from the orthonormal basis can occur with the same probability. So it's kind of an equal mix of all possible states from this orthonormal basis. So for example, for a qubit, the maximally mixed state would be the identity over 2. So for a qubit, which in terms of the 0, 1 basis, we can write as 1/2 0, 0 plus 1/2 1, 1. So this is a mixed state for qubits. Okay, so now the next question we can ask ourselves is what are the properties of the density operators? How do we know if we are given an arbitrary matrix size of the size d by d? How do we know that it is indeed a density operator and not some junk matrix? So now we will look at the properties of density operators. So again, the object that we're looking at is rho, sum over I, pi, psi I, psi pi, such that sum over I, pi equals 1, and all the states are normalized. So I claim that, and I'll show them one by one, that this matrix rho, this operator has the following properties. So first, its trace of rho equals 1. So the density operator is normalized. Why is this so? Yeah, so why is this correct? Let us look at how we can show it. So let us write what the trace of rho is. So the trace of rho is just the summing the diagonal elements of this matrix, which corresponds to just projecting the matrix, and that each diagonal element of the matrix is just the matrix itself with multiplied by the corresponding bra and ket of the row or column we're looking at, right? So the trace then can be just written out as sum over j psi j rho psi j. So this corresponds to summing up only diagonal elements. Then we substitute the rho with its expression. So sum over I pi psi I, and still we have here psi j. And we know that psi j, like so psi I and psi j are like equal if I equals j, and they are orthogonal if I does not equal j. So then what we arrive to is, so first let me write it like this, psi I psi j, pi goes out because it's just a number. Here we have psi I psi j. So this is delta ij, and this is also delta ij. And hence what we arrive to is sum over I pi, which equals 1, because the pi's are the probability distribution. They correspond to the probability distribution of the states, so they have to sum up to 1. So indeed, the trace of rho equals 1. Okay. The second property is that rho equals a rho dagger, so that the density matrix is Hermitian. This is very easy to show. Just let us look at the rho dagger. This will be sum over I, pi, psi, psi, dagger. So this would be sum over I, pi. This we just take out because pi's are real. They represent probabilities. And here what we get is psi I ket, psi I bra dagger, and it corresponds to itself. Psi I, which equals rho. Okay, so we have shown that the density matrix is also Hermitian. And the third property is that rho is positive or more in particular, it's positive semi-definite. What is the how do we show that it is positive semi-definite matrix? Well, to show it, we just need to kind of put rho in between bra and ket of some arbitrary state psi, and show that indeed the value that we get, the value of rho that we get, would be bigger or equal, greater or equal than 0. And here we will suppose that we can decompose psi, which we can, in terms of the basis of psi i's in a following way, that is just sum over I, alpha I, psi I. And now we will just open, let me say J. And now we will just open the, instead of the psi bra and psi ket, we will just substitute them with the corresponding expressions in terms of psi, in terms of the decomposition into psi i's. I have to introduce a lot of new indices, so it would be sum over k, sum over j, alpha k, alpha j, conjugate psi j. Then we have rho, which is sum over I, pi I, psi I, psi I. And then we have psi k. Okay, so let us take out all the sums and also all the numbers, which are alpha k, alpha j, conjugate pi. What we're left with is psi j, psi I, and psi I, psi k. This is delta ij, this is delta ik, which means that both j and k have to be equal to I. And hence, the only thing that we are left with is the sum over I, pi, alpha I conjugate, which is sum over I, pi, alpha I modulus squared, which is bigger or equal than 0. Because all pi's are bigger than 0, they correspond to the probabilities, and all alpha and alpha I modulus square is also obviously bigger or equal to 0. So hence we have shown that the matrix rho is a positive semi-definite. So these were the properties of the trace. Sorry, the properties of the density matrices. So again, 3 main properties, which are first that its trace, it's 1, so it's normalized, it's Hermitian, it equals the Hermitian conjugate of itself, and it's also positive semi-definite. Okay, now the last part that we're going to look at, the last topic, is partial trace. So partial trace corresponds to the following concept. So we already seen that we have a way to add a system. So imagine that you're considering a system S, and then we also want to add some other system, for example, X. Then the way to do it is to just use a tensor product mechanism. So we have a way to add a system. So if we have start with the system rho, then the way we add another system, we just add its it as it in terms of tensor product. What we also would like to do is we need a way to discard a subsystem. So for example, if we have a state on two systems, say rho AB, then we need a way to be able to map it to just a reduced state of the system A alone. And the partial trace operation exactly corresponds to what we have to do in this case. So to reduce the state of the bipartite system rho AB to just the state on the system A, we need to apply a partial trace operation. And in this case, the partial trace operation, so rho A equals tracing out B in rho AB, it is defined in the following way. So this is sum over B, say identity on A, tensor product B, on B, rho AB, identity on A, tensor product state B on B, where the B on B, the states, it is an orthonormal basis in the Hilbert space corresponding to the system B. Okay, so this is the way it's defined. Now let's look at some examples. So first example would be quite trivial, but we will go through it just to get a feeling about how the partial trace works. So suppose that we are looking at two systems, A and B, which are and suppose that their joint state is initially just a tensor product of pure states on A and B. So it can be written as tensor product of state psi1 on A and psi2 on B. And this is obviously a pure state because, yeah, we can just write it out as in terms of this particular state in their joint Hilbert space. Then the first question is, what is the density matrix of this state, of this joint state of the systems AB? Then we can write it out as psi1A tensor product psi2B multiplied by the Hermitian conjugate, so it will be psi1A psi2B. Then because the tensor product act on separate spaces, we can just reduce the action to the individual Hilbert spaces. So it will be psi1 psi1A tensor product psi2, psi2b. So now let us see what is the density matrix of the state A. Of the state A, if of the system A, if we take the partial trace of the density matrix rho AB to get the matrix rho A, like in definition above. So of course the intuition here is that because in the beginning these two, the states of systems A and B were kind of separated from each other, the operation of taking the partial trace should not correlate, should not show any correlation between systems A and B. So essentially, as they were separated in the beginning, then in the end, what we would expect is just to have a reduced state of the system A as just this part of the joint state of the systems A and B. And so let us confirm this intuition. So rho A, it's the partial trace of rho AB. So it's sum over I, identity on A, B on B. Yeah, maybe now let's label, instead of B, just I's. This orthonormal basis and the system B, let us just label it as IB. Then we have rho AB, which we can write out as psi1 on A, psi2 on B. And we still have to multiply this by identity on acting on A and ket I on B. Okay. Again, because we have tensor product in each of the elements of the expression, then we can just use that tensor product separation to separate them further. So to calculate each of the parts separately. So in the system A, we have acting identity on A. Then we have psi1, psi1A. And then we have identity on A again. Okay. So these were these three. And then on B, we have this, this, and this. Of IB, psi2, psi2B, IB. Okay, so actually so the first part of this product is quite straightforward because we have only identities. So what we left with is just psi1, A. And the second part here, yeah, and actually let me remove, to understand this better, let me write it out together with the sum here. So what is this? This is sum over I of the matrix psi2, right? So it corresponds to the just summing up the diagonal elements of the density matrix of psi2, which means that this is just the trace of psi2, and this equals 1. Because as we have seen, this psi2, so ket psi bra psi is a density matrix, and its trace has to be 1. And so hence we arrive to just psi1 on A. So indeed, our intuition was correct. And the joint density matrix of the systems A and B just separates into the matrix rho A And the similar argument can go to show that this matrix is row B. So essentially for this case, we get that row AB equals row A by row B, where row A is just a partial trace tracing out system B. Row B is just a partial trace tracing out system A. Okay, but this is very handy, right? Then kind of you can see that this state is separable. So actually this kind of states are called separable. This is not always true. So let us see an example where the joint state of two systems A and B does not separate in this kind of way. So another example, Bell state. So we already seen the Bell states. In our teleportation when we were looking at the teleportation protocol. Now let us look at it from the perspective of the partial trace and reduced density matrix. So we're particularly will be looking at the state psi, which is the joint state of two qubits, which we write out as, so let's say we have two qubits A and B, and it's a state 1 over square root of 2, 0, 0, AB plus 1, 1, AB. So 0, 0, AB just means 0A tensor product 0B, and 1, 1, AB just means 1 on A tensor product 1 on B. First question, what is the density matrix of this state? So it's psi on AB. Okay, so what will this be? So I can so here I can show you two ways to do to see what kind of state we come up with, both the matrix form and just writing out in terms of brackets. So writing it out in terms of brackets is quite straightforward. So first the ket, then the bra. Here we don't have to conjugate anything, and we end up with the following sum. So 0, 0, 0, 0 plus 1, 1, 0, 0 plus 0, 0, 1, 1 plus 1, 1, 1, 1. Okay, so this is the density operator in terms of brackets. Then how do we write this in terms of the vector matrix representation and the basis 0, 1 for each Hilbert space respectively? So again, we have this, right? And this state, in terms of the matrix, we're taking the basis 0, 0, 0, 1, 1, 0, 1, 1. So we can just write it out as 1 over square root of 2, 0, 0, 1 over square root of 2. So the first entry in the matrix corresponds to 0, 0 component, the second to 0, 1, the third to 1, 0, and the fourth to 1, 1. So we only have non-zero components which correspond to 0, 0, and 1, 1. Okay, and then we can calculate this in a way I already showed. So first we have the ket, then we have its transpose conjugate, it's in bra. Okay, and again, this vector is 4 by 1. The second expression in a product is 1 by 4. So what we get is the matrix 4 by 4. And here we just calculate. Okay, so this is how the density matrix looks like in terms of bras and kits, and also in the matrix form. Okay, now let us proceed to calculating the reduced states of systems A and B. So what is the reduced state of the system A? So we have to trace out the system B. And again, how we do it? So we have to sum, so maybe first let me write the definition. So we don't do anything on the system A, and on the system B, we need to act with the orthonormal basis. And for this case, since the system B, the basis in system B is essentially 0, 1, the sum has only two components. So we're gonna write out these two components. So the first component is nothing acting on A, then 0 on B. Then we have our state, which is 1/2 0, 0, 0, 0 plus 1/2 0, 0, 1, 1 plus 1/2 1, 1, 0, 0 plus 1/2 1, 1, 1, 1. And on this side again, nothing on A by 0 on B. Plus the similar thing. Actually, let me just copy it. It's a bit of a cheating, but I think you can write it even faster than I can copy it. So paste. Yeah, and the only thing we change is which vector we're using for B. So here we have 1, here we have 1. Okay. This looks slightly scary, but it's fine. So let us analyze the first sum. So first we act with this and this on this element of the sum. So what we get is we take 1/2 out because it's just a coefficient. Then we have 1A, 0B. Then what is 0, 0, 0, 0 on AB? This is essentially 0, 0 on A, 0, 0 on B. And here we have again 1A, tensor product 0B. Okay. So hence we just not write it here, but we're just analyzing this element of the sum separately. So I'll do it like this for this particular element, and then for the others, I'll just briefly say why it works or it doesn't work. So we end up with 1/2. Then we just separate our action again in two parts, on the A and on B. So this gives us 1. So we just arrive to 1/2, 0, 0 on A. So this first part just gives us 1/2, 0, 0 on A. Okay, now let's consider the next element, this one here. I'm claiming that this element, if it's been acted upon on the left and right with this 1 by 0 and 1 by 0, it will yield 0. Why? Because what we're trying to do here is we're looking at the product of the 1 on the system B here and the 0 on the system B here. And these two states are orthogonal. So essentially it's going to give you 0 in the product, and hence the whole product will be 0. Let me continue here. So the first element gives us 1/2 0 0 A. The second gives us 0. So this is this one. This is this one. Then the third element in the sum, this one, I also claim that it will give us 0, simply because we have 1 on B here and 0 on B here. The bra 0 and ket 1 will give us 0 because it's a scalar product. The vectors are orthogonal. So again, 0 plus the last element of the sum. Which color should I choose? This one. It will give us 0 again, because of the same reasons. Because first, here we have 1 on B, 0 on B, and also here we have 1 on B, 0 on B. It's like being attacked from both sides. 0, okay. Now let us analyze the second part of the sum, which corresponds to being projected into the state 1 1, into the state 1 of the basis on B. I'll use the same colors. So the first element will give us 0 because we have here 0 on B, 1 on B, 0 on B, 1 on B. Okay, attack again as we just discussed, attack from both sides, both zeros. Plus the next one is this, which will also give us 0 because we have here 0 on B and here 1 on B. Shame, but it's fine. Then the third element in the sum will give us 0 again, because here we have 0 on B, 1 on B. Again 0. And finally, the last element, which is this one here, will finally give us 1/2 1 1 with the same reasoning that we applied here in this case. Perfect. Then what we arrive to is that reduced state of A is 1/2 0 0 on A plus 1 1 on A. Or in the matrix form, this is just 1/2 1/2. You can see that the initial state was symmetric with respect to the systems A and B. So if we exchange the systems A and B, then the state will not change. Because so the initial state was 0 0 plus 1 1 over square root of 2. Then because it was symmetric with respect to A and B, then we can conclude that row B will actually be the same as row A. We can perform the same operation if you want. And it would be just 1/2 0 0 B plus 1/2 of 1, B. Also the same matrix. Okay, now let us look at the following. So let us compare two things. The matrix of the joint state on A and B, and the tensor product of the reduced matrices on the systems A and B. So the initial matrix that we already computed on the state of the state AB is the following. Just copy it. It's this one here. And what is the matrix which corresponds to just tensor product of the reduced states on systems A and B? Sorry. So for this, we just have to take the tensor product of these two matrices. So this will be 1/2, 1/2. Oh, sorry, not half. I cannot count, so it will be just 1/4, 1/4, 1/4, 1/4. And what we see is that actually rho AB is not equal to the just tensor product of the reduced matrices on the states A and B, which is in a contrast to the first case that we were first example that we were considering here with the pure state. When we started out with a pure state with the pure state on the both systems, and then just took the tensor product. And in this case, we saw that indeed, like the this joint state on systems A and B does separate into its reduced states on individual systems A and B. But for this case of the Bell state here, which cannot be represented as a product of states on two individual systems A and B, so the state is entangled. For this Bell state, we actually come to the conclusion that the density matrix of their joint state on AB cannot be separated into a tensor product of their individual reduced states on the systems A and B, which points out that which is indeed an artifact of the initial state being entangled, so being an entangled state between systems A and B. So yeah, so this is just to give you a feeling of like how this partial trace works, and also how it can be a bit counterintuitive for the states which are initially entangled, for the systems which are initially entangled. Okay, I think the last comment I will make today is about like the exercise sheet. So the first the exercise sheet is structured as follows. So the first exercise is about this evolution of the stationary states. You just need to apply the formula that already given you. And the second exercise is just some repetition from the linear algebra to show some properties of the trace of matrices. Also quite straightforward, or you can just look it up in your linear algebra course. And the last exercise is about calculating partial trace for the example of the double slit experiment that we already seen before. So that was the experiment where you had to see if the particle went through the left or right slit. And to do so, we coupled it. We conducted the measurement as in coupling the electron going through the slits to the other particle, which got excited if the electron would go through the right slit. So it's something that we did in the exercise sheet 6, I think, if I remember correctly. And you just have to take that state and calculate some partial traces. Okay, I think this is all for today. So it was relatively short. If there are any questions, you can ask now, or send an email, and then we can arrange a meeting during the question and answer session, or just any other time. No questions? Okay, thank you for attending. Have a nice end of the week.